we'll do a little bit of feature engineering, which is you have your data and you try to pre-process it a little bit such that it will work better when using different models. Feature engineering is part of data cleaning and organization. It's a part of the job that takes most time, cleaning data and preparing data to be ready for different models. Feature engineering will improve your data a little bit, so better data will give better models, so that's why you want to do these things. There are few things that you will not do with examples, but you should be mindful of. One is how to deal with missing values. Maybe missing values are 0, maybe they are mean, maybe they are just lines that you want to delete, and sometimes there are outliers. Maybe you want to sometimes delete outliers from your data or not, and make sure that you capture them somehow. What we will do is log transformation, one-hot encoding, and scaling. Log transformation is something that makes your data look more normal, more like normal distribution. Right? If you have data that are skewed a lot on one side, for example, here is a salary. If you have a new salary, then there is a lot of people who have some number, let's say over there is maybe 80,000, and then as you get out to higher numbers, you have a long tail, but not that many entries. So what you can do is look at the logarithm of the numbers instead, and then if you take a look at the logarithm, maybe the numbers are slightly nicer distributed, as you can see on the right. It's fairly easy to do with a scalar. Log transformation. First, here is a little piece of code that creates the data. We'll use synthetic data. So here we import NumPy, then we import the function transformer, which we will use for the log transform, and then Python for creating plots. Okay. First, we set a random seed for reproducibility. You can say that you would like here any fixed number, and if you have a fixed number, then as if you have the same libraries, you will get the same outcome. Right. And here is X, that is exponentially distributed data. Say exponential distribution, you can say scale, how many, and so it will be 1,000 of them, and this is used if you have a lot of small values, but sometimes you can have large values like long tails. And here I will plot the data, visualize it with a histogram, 30 bins, and let's see how it looks. So here are the data. I have value from 0 to 80, and here is how many times each of the value was attained. Okay. Now in this form of data, most of the data is here around 0, and then kind of distribution looks like this. And what we would like to do is have it look more like normal distribution, so we can try to do it. So I will create log transformer. This doesn't matter if I misspell it. I will function transformer. That is the thing that we imported, and here is a function that I am trying to use. We will use logarithm. Let's see if I misspelled it, maybe not. Now I can show how X looks like. So it's an array of numbers like that. and now we try to do xlock lock transformer or transform x, right? This lock transformer. I cannot spell it. I'll fix it like content. Okay. Now this is the transformed data. You can we try for a b in zip x lock print ab. Now you see the original number and the lock transform number. Right. Maybe this is not very useful, so I will try to do a plot. Show the first one and make another one. Visualize the transformed. Distribution. Transform data, and should maybe make it a different color. Right. Oh, well, plot show. Let's see. This is the original data, still the same. And now the transform data, also the same, because here I have to plot xlock and not x. So original data, this transform data. Now it looks more like normal distribution. One hot encoding is way how you can take categorical data into numbers. So first is, if you have a category, let's say country, Spain, France, Germany, you can of course change the category into number. You can change them, write them as numbers. Spain 0, France 1, Germany 2. The problem with this somewhat is, if you are trying to use the country ID in some regression, then you may have some interesting algebra there, saying, for example, Spain plus Germany is 2 times France. I don't know, if it seems suspicious, right, to make an assumption like that. Create a data frame that has some categorical column into column that is numerical and that is easier to process with machine learning. So here is a data frame, and it has in its IDs, whatever that is, and a country. You like the country to be a numerical value. So first thing we could do is make each country a number. So you can do it, call this panda factorize, and I will have here the data frame, and I will take the column country. Now it tells me if I want to change the country into, maybe I should still my data frame here. Well, if I want to change the country into number, then I can say Spain will be 0, France will be 1, Germany will be 2, here is the index, and this will be how the column for country should be changed. So it would say that the column for country would be 0, 1, 0, 2, 1. You can also assign it in. Comment this out, and I will say I'll create a new column, country ID, and I put there this series. Right. Okay. 0. It's a tuple. The first one is the it I need to put in. Okay. And now I have the data frame, and I have country as the categorical value, and now country ID is a numerical value. Suspicious thing here is that 2 times France equals Germany, or things like that. Right? So if you want there to be some algebraic operations that make sense, you have to be careful. So another feature that you can do instead is that you call it the function getDummies, and instead of the category, it will create for each one possible entry in the category, it will create a 0, 1 vector that will say 0 or 1, whether the particular line was in the category or not. So here is country France, country Germany, country Spain, and you can see that each row has exactly 1, 1 that corresponds to the state or country for each row. Right? When you do it like this, sometimes algorithms may be a little unhappy because there is a little bit more dependence than necessary. If you look at the last column, you can erase the last column, the country Spain. It's derived from the other 2 columns. You could say that the country Spain is column of full ones minus country Spain, country Germany. So you have some linear dependence. Right? So if you only know that you have 3 countries, France, Germany, and Spain, when you tell me that you are not France and you are not Germany, then I know you are Spain. Sometimes the extra column is deleted, some algorithms require it. One hot encoding. Here for this example, I created 2 categorical columns, country and food, to make it a little bit more entertaining. So how does it work? From pandas I call get dummies, and I can put in the data frame. Bam, there it is. For each of the categorical columns, country and food, it creates new columns where you have true or false for each of the different categories, if it is there or not. Right? So each of the country and food has exactly 1 entry that is true, 1 entry that is true, which is indicator variable, you can call that for the original category. Right. This creates linear dependence, right? Because from these 2 columns, for the food, pizza, food, bread, you can derive what's the value in the last column. So what you can do, if you want, you can write here drop first, true, and if you do this, now one of the categories is missing because you can derive it from the other 2. So for machine learning, sometimes this is useful. So get drop first, removes 1 category, can be derived from the other 2. Right. Another thing that you can do is okay, I'll leave the first one there. You can say which of the things you want to change. So here I can say prefix, and I can say that the column country will be, this is a dictionary, be written as C. Did I mess up? And then the column food will be called F. Okay, so now it's smaller labels. You can change what the label is if you want to. Okay. You can also do change the label. You can also do df dot country. You put there the one column, and it will create a split just for this one column. If you want to add a prefix, you can add a prefix. Okay. So if you want to do it just for one column, you can. You can also do it for the whole data frame and change the prefixes, or you can do it for the whole data frame and have the prefixes having the original name and drop first if you want to use it for machine learning, may be useful. If you have data, here for example weight and height, that have different units, and you would like to do something like k nearest neighbors classifier, right? Then you are trying to calculate distance between the data points, and if you have different units, then the distance may be kind of weird in a way, right? So let's look at what we have here. So we have people that have height 5 foot or 6 foot and weight 160, 161, 180 and 185 pounds. Okay? And it's a question, who is more similar, 0, 1 or 2 and 3? Okay? Which people are more similar? So if you look at just the data, then 0, 1 are kind of close, because in height the difference is 1, in weight the difference is 1, right? So the Euclidean distance would be 1.4, which is very close, right? Compared to the 2 and 3, which have the same height, but the weight is off by 5 pounds. So in Euclidean distance, they would be in distance 5, right? So 2 and 3 is further away from, further apart than 0 and 1. Okay? And of course, if you ask yourself a question, which two people are more alike? Two people that have height 6 foot and one has weight 180 and the other 185 pounds, or two people that have same weight, almost 160 and 161, and one is 5 foot and the other one 6 foot. Okay. I guess that the people 2 and 3 would look much more alike than the people 0 and 1. 0 and 1 of them would be by 1 foot shorter, and it would be very easy to notice, and maybe for the same height the weight would also make it look slightly different for the body. So maybe you need to adjust the units a little bit, right? So, and for that one can use standard scale. Here is a standard scaler where if you have the data, you fit the data and transform it with it, and suddenly if you look at the data points, the 2 and 3 are much closer than 1 and 2. At least if you look at the picture on the right, it's obvious right away. Picture on the table on the left, maybe it's not as obvious, right? No, the standard scaler scales the data points you have into standard units, which means how many deviations are you away from the mean. Let's give standard scaler a try. So here I have a data frame with weight and height. This is the data frame printed. Right? I can try to draw a picture of it using Seaborn. Sometimes things are easier when they are plotted. Scatter plot x weight and y is height. Alright, let's see. Right, now we have a scatter plot. So now you can see that these 2 points are kind of close to each other. These look far away. You can also see that the numbers here are increasing much more than on the y-axis. So we can try to make it such that 1 unit here is 1 unit here. So I will copy this picture, say g set aspect 1, and now it is in the same 1 unit on x-axis is 1 unit on y-axis. Now you see these 2 points are much closer to each other than these two. So if you try to do something like k nearest neighbors, you will have these 2 points much closer to each other. But in height between 5 and 6 foot is maybe bigger difference than having same height of 6 foot at weight 180 or 185 pounds. So we would like to kind of present the data like it was presented here, right? So I'll try to do that. We'll use standard scaler for it. So how do you do standard scaler? I create object, this is the scaler, standard scaler, right? It doesn't do anything. So what I need to do is scale the data. So I do scaler, and there is a function fit transform that will transform the data that I put in. It calculates the mean, standard deviation, and scales all the data. Right, I will call it here scaled df. So little problem with scale df is that it is to the array, but the data frame was a nice thing that has weight and height. So I would like to create a data frame out of it, maybe. So what you can do is you can do p.data frame and put the to the array in it. Now it's nice matrix. Right? It would also be cool if we have the column names at the columns, and just copy the column names from the first data frame. Bam! Now we have a data frame that contains the scale, weight, and height. Okay, so I call it df scaled. Right, we have it. And what I would like to plot it. I'll print the df scaled. Now I'll try to plot it. I will copy the plot from up here. And the input data I put in the df scaled. And now you can see that the weight and height is number here like -1, 1, -1.5.5, and now these 2 points, it was corresponding to the 180 and 185 pounds are closer to each other than these. So maybe the k nearest neighbor will work on the scale data much better than before. Right, and maybe here is another thing. What are the parameters of the transformation? So when you are fitting it, it will tell you what the mean is, scalar.mean. Okay, mean. So those are the means of the two of the weight and height, and scalar scale. So for each of the columns it will tell you what the scale is. Print. So this is how much you scale the number, and this is the center. You can of course look at the df.describe, and if you look at the df.describe, you get the mean, the mean is the same for the weight and height, and then you have the std, which is slightly off because of the dividing by n or dividing by n minus 1. One of them is the standard one, and one of them is for the sample. Here is the formula for standard scalar. So you have your samples, and samples, you calculate the mean, which is just the average of the samples. Then you calculate the standard deviation. So for each sample, you take the difference from it as xi minus mu from the mean, you square it, you sum them up and take the average of these. That is the standard deviation squared, and you take square root of it. Right, so now you know what's the standard deviation from the mean, and then for each entry that you have, you take the value, subtract the mean, so you know how far away you are from the mean, and you divide it by the standard deviation. If you follow the units of standard deviation are the same units as units of the mean and units of the x. Right, so if you would say in kilometers, right, so, or maybe miles, it's more miles, so we have x miles minus mu miles divided by sigma miles. But the miles will cancel, and eventually we'll have a number that doesn't really have units, just how many standard deviations you are away. And now the numbers are slightly better for comparing between different units. By hand, for the column weight, is a little reminder what are the variables we need to get. So we need to do mean. I can get mean by looking at the data frame, the column weight, and calculating the mean. Bam. Okay, we have the mean. To make it easier, I remember that there were 4 entries, n equals 4, and then I will need to calculate the standard deviation. So yes, take the weight and calculate the standard deviation. So when you use the weight standard deviation, it will give you a sample standard deviation, which will divide by 1 over n minus 1. So this is sigma square is equal 1 over n minus 1 times the sum blah 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 blah. Right? Okay, xi minus mu square. I can write it all. And I want to calculate version where I have n in the denominator, not n minus 1. So what I need to do is I need to multiply it by n minus 1, which is I am cancelling this thing, and divide it by n. Right? Recall that this is all under square root, right? So if I just want to calculate sigma, and this is square root of this whole thing. So I need to multiply it by n minus 1 over n square root, so to power 0.5. Alright, now I have my std. Okay. Alright, I can try to do print mean std. These are my oh, it was probably bad. I have to write std equals mean and std, and I can compare it with what the scalar was doing. So print scalar dot mean and scalar dot scale, right? And the mean was the same, and now the standard deviation or the scale is now the same as well. Right. And now I can scale the column weight. How do I do it? I subtract the mean, unexpected indent, subtracted the mean, so now it's split up, and then I divide by the standard deviation, and tada, I have my data. I can print it, and I will also print scaled weight. So this is the data that the scalar created, and this is the data that we created by doing it by hand. So this is trying to show the algorithm is not hard. You can do it by hand fairly easily, but you don't have to. You can just use the standard scalar instead. Right? So it would be nice to see it demystified. I recommend looking the standard scalar and one-hot encoding and look encoding for the stat quest. Now that we learned how to pre-process the data, we can try to do the diamonds problem again. We'll try to build a model predicting the price of the diamonds, but maybe now this time we can use cross-validation to see how the models are good and maybe see if the standard scalar will help us. The question of predicting price of a diamond, this time we'll try to add a little bit more data processing to it. Okay? So remind me the question. Question is, you are trying to buy a diamond, and I will tell you that I have one for sale. It has 35 carats, ideal cut, color E, clarity, depth table XYZ, whatever these are, and I'm offering it to you for $2,000. Do you wanna buy it or not? Right? And so you get the data set, and we'll try to work on the data set to predict what should be the price. Alright, so here we load the data frame when it loads, and we have hat. Right. So this is the data frame. You can see what the columns are there, unnamed. The first column looked like it's not a great column, right? It's just the index, so maybe we should drop it. Drop, and let's call the first column 0. So now the first column is dropped, and I copy the data frame. Okay. So now I have my data frame ready, and other thing I would like to do is maybe change what data we have in the data frame a little bit. What it will be doing in task 2. Work on the data a little bit. So I have my data frame, and you can see there are some categorical values. So I will try to change them into numerical. So is this pd dot get dummies df. Now it will look like it's one hot encoding. Life is great, right? If you want to just see the name of the columns, you can put columns and you see what are all the column names. Okay. We'll see data frame is equal to maybe copy it for future generations. Okay. Put columns, and I will copy the data frame. Another thing I would like to do is remove all the entries where the price is more than 3000. So if price is less than 3000, and I have this 0101, and I can have data frame restricted to this. So now all the prices are at most 3000. I do it because I expect that the cost of the diamond will be about 2000, so I want to remove big outliers. So I hope this will make it a little better prediction, right? Normally you don't want to do it if you want to predict any diamond, but maybe in our special case we will do this. We'll try to do that we split it into training and testing. First, what are the it's x and what is y. X it will be everything except the price column, right? Price is the thing that we are trying to predict. df drop columns price. All right. Now I see x is okay. Price is not there. And y will be just the price. No. Right, this is y is the price. Right. We have x and y. Now I will use standard scaler to process x. Scaler is standard scaler. Do it so I can use k nearest neighbors or things like that. Scaled x is scalar that we fit, and at the same time transform x. I can look at scaled x. Okay, it's in the form of an array, so I would like it in the form of a data frame, so I can use data frame, put the array in. I have it like this. It would be nice if there were names of the columns, so I will try to copy the names from the original. Alright, now it's good. X is equal to this. Right? So now I have my x and y variables. Now I do the train test split. Train test split, so I will have X for training, and then I will have X for testing. Train test split, X, Y, test size 0.2, random state, you can write whatever you want, and here now it's split into training and testing. I have to remember them. X train, X test, X train, X test, Y train, Y test, Y test. Right. And now I have the data split into training and testing. Notice that I did the standard scaler on all the data before I split it into testing and training. Right? You can do it on the training, and then you have to rescale testing later, also an option. Training data, we will explore several models and see which of them does the best, and that will be the model that we will try to go with. Here are a few models. I will try to create them all in linear regression, okay. We have one of them created. I will create neighborhood 2. It's a k neighbors regressor, and neighbors maybe 2. I would say what 258. So I'll do 258, 58, 258. Okay. Now I will do a list, classifier and names. So I will have linear regression. Make name linear regression, and I will do it for all the classifiers that I have here. So for the regressions that I have here, the idea is if I do this, then it will be easier for me to loop through them, right? So make 2, and I'll do 5 and 8, 5, 8, 8, 8, 5, 5. You can also do any other number that you like here, like for the number of nearest neighbors. Right. So we have the model. Maybe we should model. Right. So now we will do for model and the name in this model name. We will try to do cross validation. It will create the k-folds and calculate some metrics for us. Life will be great. So let's see. Cross-val score, and here's our model, and X train. The values Y train, and let's see if this runs. Maybe. Okay, it ran. Print. And we should maybe say name model name. Right. And maybe we can also be more specific about what scoring we want. And call this R2, because for R2, remember, it's a number that is 1 or less, closer to 1, the more accurate it is. It calculates the squares of errors and says how much better it is compared to the just mean average mean, and so higher is better. All of them are pretty nice. We can also try to do other scoring models. For example, we can do negative mean absolute percentage error. Alright, so let's see how to spell it correctly. Negative mean absolute percentage error. Okay. It says what's the error in percentages? So how many percents are the prices of when you look at the model and when you look at the actual number? So looks like the mean, if you do the k-nearest neighbor, is a little better because it's closer to 0, larger is better. And then we can also do how much is the negative root mean squared error. And now this is error in absolute value, so maybe error is about $180, here it was $270, it depends on the font that you look like. Here the error is $191. Model name is R2. Percentage and this is absolute. So now you have some idea how much the models are off. Right? Maybe the absolute and percentage is better way of seeing it. And our question is, which of these models do you trust most? Right? If you look at the scores from the cross validation, maybe looks like the numbers are, well, I don't know. Yeah, all very similar. So we have to pick one. But, that were there, you have to pick which one is your favorite. So for me, I think the neighbor 5 looked good because the mean error was not too big in the absolute value. Maybe it's what I care about. So we have this model .fit. We will put there all the training data and the model is fit, and I will try to test it on the testing data. My bread is model just predict x test, so it doesn't complain later. So now I took the testing data and tested the model. Now the model is tested on data it has not seen before, and let's see print I will do R2 score. So R2 score, almost R2 score for y test, y ret. Let's see, 0.93. Nice. I will do the mean absolute error and the relative error. Mean absolute error, and here's mean squared error, y test, y pret. Yeah. Now the number is much bigger than were the numbers before. We had numbers around 180, that's what I was hoping for. Now the error is 30,000, and here the error is squared, right? And I would like absolute, so I will take a square root of it. Okay, now it's much better. It's about what I was hoping for. Print mean relative error. And what's the mean absolute percentage error? Y test, y alright, right. So I have error of about $170, and the relative error in the mean is about 10%. Right. So now I have my my model, and I'll have to try it on the actual data I am trying to predict. Prediction. So I will look at the. I have to make a vector that contains the data about the diamond I have. So X train. Look what are the columns here. So these are the columns. So I have to make is the one that you want to predict. You want to predict just one. Then we go carat 0.35. Depth is 61.5. Then there is table 55.0, x4, y4, z 2.5. Cut. What is my cut ideal? So cut fair, no. Cut good, no. Cut ideal, yes. Cut premium, no. Cut very good, no. Color D, no. Color E, yes. Color F, no. Color G, no. Color H, no. Color I, no. Color J, no. Clarity I, no. Clarity IF, no. Clarity S1, no. Clarity, no. VS1, yes. 1, 2, 3, 3 more zeros. 1, 2, 3. Okay. So here is the data that I need to use for prediction. Right. Before I do that, maybe what would be good is to rescale it, but maybe let's try to check if I made the right thing. Len columns F28, len first one 26, 26. Alright, good. So at least the length of the vector is the same, so I have a chance. So I have to rescale this with the standard scaler. So I had the variable scalar that I fit before, and I used it to process the x vector. So scalar transform x1, that's what you want to know. X1 equals, okay. I'll rescale the data, and now I can try to call model predict x1. Alright, so model claims that the diamond is worth $500. So maybe not looking promising that I would manage to convince you to buy it for 2000, right? There's one more thing that you can do, and that is you have your model, that is the neighbor 5. You can also, before you do the prediction, you can fit it with the whole x and y, all the data you have. Right? This is a thing that's somewhat optional, because some people think it's a good idea to use all the data you have for the training, because you may get more accurate model. On the other hand, if you use only the training data and the testing data, then you had a way to verify how good your model is. Now you don't have the guarantee test that was there before. So anyway, I do it with everything, then $515. So anyway, that we need to predict, it has the specific cut, clarity and color. We can try to restrict the data only to the diamonds that have the current cut, color and clarity. Here is a little attempt to do it. So here I have the data frame that I download the data and put there the x and y. Here in x I have to drop all the categorical columns. Right? Maybe I can do, yeah, dfb.head. So there's the categories that I have to remove before I do it into x and y. Right. I'll ignore the train test split, and we'll just do scaling. We scale the data, the x, and we just try to see what the models would predict. Right? So if you have linear regression, I have the other models ready too. I'll fit it. This is the numbers I want to predict, and predicted price 1800. Right? That's maybe better, looks more reasonable. It's not quite 2000, but maybe we can talk. Right? So here it looks like if we select only the cut, color and clarity, we get a number closer to what I was hoping. Right? If you look at the different regressors, we are back to $500. Maybe the linear regression is just very bad at approximating this data, because 6 is better, because maybe the data is not linear. Is from the slides that will be on the future presentation. That is the PCA, Principal Component Analysis. So what it helps us is to look at the data that have high dimension and transform it into low dimensional data, or change the dimensions, and hopefully the variance in the data will be only in 2 dimensions or something like that, right? So I have my data, and I will fit and transform them with my principal component analysis, and then I will do a scatter plot of my data points, where the first 2 values of the X transform will be used in the scatter plot, right? And then I will add the one point that I wanted to look at. So I'll try to execute it, and it plots all the diamonds that there are in the data set. So here you can see the pluses. Each plus is a diamond. The price indicates how costly they are. Alright, there is one outlier out here. But other than that, it's nicely concentrated, and you can kind of see that the price is, well, okay, maybe the diamond is close to the diamonds that are kind of cheap, right? The one that we didn't know. Another thing that the principal component analysis has is this explained variance ratio. What you would like is that you see something like a L-shape graph if the PCA is good. So this is not quite L-shaped, but the first 2 components are kind of large compared to the remaining ones. So that is good. It means that the picture you see here explains a lot of how the price is created. So that will be in the next presentation explained more carefully, but I thought these are fun things to see, and it is a way how you can visualize the diamonds in 2D even if it is high dimension. So as I would show it to you now.